तो अभी तक जब हमने जितनी भी SClO2 के टॉपिक्स किए हैं उसमें हमने ऑसिलेशन को कवर कर दिया, ठीक है। और ऑसिलेशन में हमारे पास दो मेजर एग्जांपल थे। एक क्या था? स्प्रिंग मास, और दूसरा सिंपल पेंडुलम। और सिंपल पेंडुलम के बाद हमने भी देखा कि जो रियल पेंडुलम है उसको भी आप अगर मॉडल करके कोई ना कोई अप्रोक्सीमेशन करके उसको भी कर सकते हो। एग्जैक्ट नहीं होता, बट यू गेट द मैन आइडिया। सो दे आर बोथ एग्जांपल्स ऑफ ऑसिलेशंस। और जो सिंपल फॉर्म में उसका हम सिंपल, सो दे आल्सो गिव अस सिंपल हार्मोनिक मोशन, because it's not just oscillation, because oscillation can be non-simple harmonic, yeah, because simple harmonic has certain strict requirements. But whether what is a simple harmonic or not, oscillation has one thing in common, that it's a single object, yeah, which has this back and forth motion around one equilibrium point, right? That's the main thing. So because the equilibrium point can be used to locate that whole system, you can safely say that the system as a whole is not oscillating, right? Only parts of it, like the particle or so it's only that is oscillating, and the system as a whole must be in equilibrium, and that has two possibilities. Either the system is at rest, or it's moving as a whole. So you can have this simple harmonic motion inside, for example, a car, a moving car, or a train, right? It will still be a simple harmonic motion. So now, so you can easily see that all this phenomena, all this disturbance is localized around one point. So imagine that what happens if this oscillations actually is propagating. So it starts somewhere, but there is some mechanism. So far we don't have any mechanism. Why? Because our system, both these examples, it's isolated from the rest of the world, right? It's not interacting with anything else. That's why whatever happens, it happens in that same area, and all the outside world is not affected, right? Hello. So now, because this is isolated, so there is no way for this disturbance to propagate. So now you need to imagine what if there is a mechanism which allows that, right? And I'll start with a very simple mechanism. I'll get to this later. So let's say I have this spring mass system, right? Let's say it's fixed there, so nothing is possible on that end. But let's say you start this motion, you give it some initial kinetic energy, and it starts motion, or elastic energy. And let's say there, instead of one, there is an array of such springs. So there is the one next to it, and then the one next to it, and they're just connected in some way. So now what will happen? Let's say you start that oscillation right there. What do you imagine? The one touching it in contact. You have studied in. Okay, so because we learned in the very first CLO that whenever there are two objects interacting with each other, that interaction you can model that interaction as force. Yeah. So this disturbance will immediately transfer to the next one, and then that disturbance will transfer to the next one, and then you have a propagation, right? But of course, we don't want to do it that way. I mean, that is also possible, but typically nobody uses the word wave for that, right? You think of it as many oscillations, simultaneously. You can think of it as a multi-oscillating system. The terminology, I'm not the one creating this terminology, so you cannot ask me why, right? So in that setup, nobody will use the word wave. But if it happens in some medium like water or string, or a metallic rod or whatever, space, because you cannot pinpoint those atoms and molecules. So the word coined by physicists for this phenomenon is then a wave. So now, if I ask you what is a wave, it is a phenomena in which one oscillation somewhere, right, when you create it, it has a chance to propagate, in some direction. And what is allowing that? There is some medium, right? But the problem, what do you mean by the medium, right? So the waves which we are familiar with, there we typically expect a medium which has atoms and molecules. Yeah? So that anywhere you have this oscillation, initial oscillation, because there are atoms and molecules and bonds, and they behave. You all. So now you know why this model is so important, because the bonds, they behave like springs, and the atoms behave like particles. So this springiness and this particleness is already there. So if you have this a medium full of these atoms, every medium will have to be full of those atoms. Yeah? So you naturally have this mechanism, and you call it a mechanical wave, right? Why mechanical? Because the interactions are mechanical. Yeah, elastic energy, kinetic energy. Although you don't, interestingly, you will never call it elastic energy and kinetic energy. I'm using these words only to explain the phenomena, right? Because it's happening inside microscopically, you have no control. So it's still mechanical energy, but you will call it wave energy. So if I now ask you three types of mechanical energies you learned so far, you learned kinetic energy when the system as a whole moves, right? Yeah, moves or vibrates. So that particle, this particle oscillating is also has kinetic energy. It doesn't need to be in one line or in one direction. So then you have elastic energy, gravitational energy, and now you have wave energy. So wave energy is also kind of mechanical energy, right? So and you see, you have seen this example. You just throw something in a pond, and you see these ripples. So what is responsible for this ripple? The fact that water is a medium, and those atoms, they actually carry this energy, right? This is the main idea. But before I get to the details, you are already aware, and of course you have these transverse waves and longitudinal waves. You also know that, yeah? You must have heard this in school and colleges. But then there is another possibility where there is no medium, and still some disturbance can travel through space. Do you remember that? Yeah, electromagnetic waves, right? So the space, the free space, has no atoms, no molecules, no stringy bonds, but still possible. So what is responsible for that? No, radiation is the thing which actually travels. I am asking for the mechanism which replaces the medium. So what does space have? Space must have something. If it doesn't have atoms, it must have something which allows that propagation, and that something is fields. The electromagnetic fields, electric fields, magnetic fields. Electric field is not a thing, right? It is not a thing. Magnetic field is not a thing. It is just a property of space. So even if there is no matter, even if there is no charge, so the reason field is important, that if I take you to, let's say, two regions in space, imagine two regions in space. One region has free space, but it has no fields. It's just free space, literally nothing. And there is another region in space, again empty, no matter, no charges, nothing, yeah, no bonds, but that has fields. Now, material wise, they are both empty, but they have different properties, right? And to remind you, you have already seen some of the properties, like permittivity, the epsilon, permittivity of space, similarly permeability of space. So interestingly, I have to change my argument. Even when there is no field, yeah, that permittivity is still a property of the space, right? So even the free space has those properties. It means, and it has permeability, mu naught. So free space has permeability. So with those two properties, any region of free space allows you to set up an electric field or magnetic field in it. You still have to do it. The free space cannot create it on its own, but it has the potential to actually absorb that field. So if you have some mechanism, you just launch that mechanism, and the free space. So the free space, and that is the reason why electromagnetic radiation is possible. Yeah. So now you have all the possibilities covered. So let's get to. So now you know that we want to understand traveling waves. Traveling is actually, I mean, you don't even need to say traveling, yeah, because wave by definition has to be traveling. Yeah, that's the difference between oscillation. Oscillation doesn't travel, wave travels. So this traveling wave, actually, I don't think you need this. This is only for clarification. And you definitely need a medium for mechanical waves, right? And then you have transverse waves. So, okay, the particles of the medium must move in some way for this propagation to be possible. So, there are two modes. One is transverse and one is longitudinal. Transverse means that the propagation is through the medium. Okay, the propagation will be through the medium in both transverse and longitudinal, right? Because the medium has to carry the wave. So, that is common. What is different? The individual particles have to move perpendicular to the, you don't need to say up and down. Up and down is only for water and string. What if what if I have a string which is like, yeah, from top to bottom, and I do that. This is not up and down, yeah, this is sideways. So never use a word which is actually limited. So it's actually perpendicular to the medium. If the motion is perpendicular to the medium, think of the medium as a plane, right? Then you have transverse waves. So if the ये क्या हुआ इसको? So if the individual particles move in the plane, right, along the propagation in the same direction, in the same plane, I wouldn't say direction because it has to, yeah, it has to, the particles have to oscillate. So one thing is a must. All the individual particles, whether it's transverse wave or whether it's longitudinal waves, the individual particles must be oscillators. There must be oscillators like that, because without oscillation, wave propagation is not possible. So you can think of wave as an infinite, yeah, collection of oscillators, right? But to be called a wave, it's important that the disturbance starts at one point and then the medium actually helps it, right? So can you give me an example where I have a bunch of oscillators, they all oscillate and sync? Okay, another requirement is that they must oscillate at the same frequency. It's not possible that they oscillate at different frequencies, right? So why? Because the disturbance is the same. Because they all originated from the same disturbance, so they must oscillate at a common frequency. So what if I create a large number of oscillators? They all oscillate at the same frequency, but I will still not be allowed to call it a wave. Can you imagine a situation? What if I have an array of people, right, or sources, and each one is responsible for making each oscillator move, right? So I still have an array. So think of an infinite number of demons, and each one is just moving one, yeah, atom. This will not be called a wave. Why? Because it's driven. It's driven in everything. So they are not actually, it's not a propagation. Yeah? They are just, this just happens to be oscillators, multiple oscillators in action at the same time. In order to be called a wave, there must be an initial disturbance, and then the medium must be carrying the energy. Yeah. So you cannot just have a list of people and actually they start moving things and you say, oh, it's a wave. You will not call it a wave, right? So of course, people in loose language, they still use the word wave. For example, I mean, you can call it a wave in one way. If the information, let's say, have you watched a cricket match or a football match in a stadium? And you know what happens there? That let's say somebody decides to create that wave of, yeah, waving hands. So there, although each individual is providing the energy, so in that sense, you will not call it a wave. But if you change the perspective, then you will call it a wave. Let's say one person decides to have that phenomena. So you can think of that as the initial, yeah, stimulation, and then every individual is just playing its part. But strictly speaking, because the energy comes from the individual, so the strict definition will not allow it to be called a wave, right? Wave, in order to be called a wave, the energy must start from one end, right? So if each particle is providing the energy, then it's not a good idea to call it a wave. People still call it wave because they are not precise in day-to-day language. Abhi samajh aa gayi baat? So now this diagram clarifies this picture. The initial energy is provided by this agent. Yeah, you need an external agent, and then you actually, and I mean this. Achha, one more thing, one other difference between a wave and oscillation. In oscillation, In an oscillator, you just need to interact with it once, and then the rest, you don't need to keep interacting with it, right? Because this is an oscillator system, the total energy is not changing, and it will keep oscillating unless there is damping, like resistive forces, damped oscillation. But in this case, it's not enough to just wiggle it once and then leave it, right? You have to keep doing that. Yeah? So that source of oscillation still has to be at one end, and then the medium will be responsible for propagating it. So you can now easily see that this part of the medium is in oscillation. I mean, it's not physically touching this part, but because there is a medium, so that disturbance is actually traveling. Don't think that this is the only mechanism which is possible. This is the one which you see, right? Which you can see easily in an experiment. If I now ask you a question, what if instead of doing it this way, what if I try to pull this string? So what will happen there? And let's say you are at that side. Yeah? Do you have any short string with which I can demonstrate this? Yeah. Can you come here, please? Now you need to answer one thing, right? Hold that. Okay. Yeah. So if I'm pulling it, yeah, that hand will feel actually. So we call it tension, right? So in that chapter we just call it tension. Calling it tension doesn't solve the problem, right? Just like Newton said, action, reaction. Calling it reaction doesn't answer the original question. It's still, you are still not telling me where it is coming from. You are just giving me a name. Yeah, just like I told you the examples of scholars. Yeah, you go to them and you ask something, and they will just coin a difficult word from Arabic, but that doesn't solve the question. Yeah, they still have to explain it. So the question is that calling attention doesn't solve the problem. How does this disturbance from my hand reaches there when I'm not physically touching it? I'm only touching the string. He's only touching the string. So it's actually a wave. It is a wave. It is a longitudinal wave. Yeah. And without this medium, and if you don't trust me, remove the string, and then I want to see how you do that. Yeah. So it's a longitudinal wave. Because we don't see it, we never notice it. It's the same phenomena. This is transverse, that is longitudinal. So the reason you find it unusual is that you study, because all your understanding comes from chapters. I studied this chapter, and then I studied that chapter, and then you switch off your brain. There are things which you have to infer yourself. So you studied longitudinal waves only in the context of sound, yeah. So you start believing that sound is the only longitudinal wave, right? Yeah. I mean, you just happen to study that. That doesn't, I mean, rule out other possibilities. This is a mechanical wave, right? And it's a longitudinal wave. So all the forces are transmitted by these members through, and I'll give you one more example of water, because you saw water, yeah. You turn off. I mean, when you want to take a shower in the morning, what you do? You turn off the water tap, and the water is in the tank. So immediately, the moment you actually turn that water tap, immediately the water comes out. It doesn't have to travel from that part to this part. So what makes it happen so quickly? If the pipe is full of water, no matter how long the pipe is, the moment you open the valve, the water comes immediately. So why doesn't it need to wait? So what is happening right now? It's the wave. It's the water wave, pressure wave, right? So because it can feel the pressure immediately, right? And you remove that pressure, and the pressure will immediately, you will see the difference. Although the pipe is still full, but you immediately feel that, okay, something is wrong there, right? So it's actually, both these are examples of longitudinal mechanical waves, right? So longitudinal wave, now you know when the particles in the medium move parallel to the direction, and there it's normal or perpendicular. And you can see, yeah, he has given you the example of that spring mass. So this is only a model. In reality, you have those atoms and bonds. Okay, so people have studied this phenomena. One more thing, although we speak of propagation, uh, but we will never use the word velocity for propagation. You will not say velocity of propagation. Why? Of course, it has a direction, right? But there is a reason for calling it speed. Because it's very clear. Whenever you have a source, it will always travel in only one way, right? It will always move away from the source. Yeah, and it can, if the medium allows, it can travel in all directions. The reason in string it only goes one way is because the string is only there. If you have those strings everywhere, then it will start everywhere. So because we know it's always outward, so there is no point in attaching direction to it. So it's the same with current. Yeah, have you thought about electric current? Yeah, the charges are moving, right? But you never say that current is a vector. Why is current still a scalar? Because it will always be in that circuit. It will never leave out, for example. Yeah? So because we know the wave, the propagation is always out, away from the source, and into the medium. So we will just say speed of the wave in a string, right? V string doesn't mean speed of the string. So remember, although parts of the string are moving and up and down, but that speed of the individual particle, that is what you study in oscillations in chapter 15, right? Every particle will have its velocity up, down, or right, left. But here this symbol V is not the velocity of the individual oscillator. This speed is the speed of the overall propagation, right? So it's how the energy travels in the medium. So people have studied strings, and it turned out, somebody has to remind me for the quiz, right? We'll need 10 minutes for the quiz and 3 minutes for distribution of papers. So if you have tension in the string, because without tension, you cannot have a wave. Can somebody explain that? I have a string, and that string has no tension. Why can't it have a wave?
Because there is no force pulling on either side.
Yeah, but you're discussing the endpoints. Yes, this was. Yes, you need the energy to travel. So the individual oscillators will need to have both the elastic energy and the kinetic energy, right? Because after all, it's a collection of oscillators. Each oscillator must have two forms for oscillation, because without oscillation, you cannot have a wave. It's clear, right? If there is no oscillation, there is no wave. And you know oscillation requires both forms of energy, kinetic energy and potential energy. For kinetic energy, you just need atoms. That's there. The string has atoms. But for elastic energy, there must be a force throughout. So without tension, there is no hope to. So and this mu is actually not the mass of the string; it is the mass density. And this is not. I mean, when you say mass density, you say mass divided by volume, right? But because it's a string in one dimension, so it's mass per length, right? Mass divided by the length. That's called linear density. So the density which you are used to so far, that's actually called volume density, yeah? Or volumic density. This is linear density. So if you know the linear density of a string, and if you know the tension in that string, somebody has worked this formula that if you take the ratio and then take the square root, that will give you. For you, it's not important to derive the formula because this course doesn't have that derivation in it. It's a bit advanced. It's still possible in advanced courses, but not in this course. But what you need to know is to understand the meaning. What does it mean? Tension in the string, linear density of, yeah, and why do we use density, not mass? Because mass will be affected by how large the string is. Yeah. So mass depends on two properties: material and how large it is. Right. We don't want the size of the string to play any role here. Yeah, I mean, what happens is that only the material decides. So it doesn't matter how large or how small or how, right? So it's mass per unit distance, mass per length. I would not say unit, mass per length. So it means that the cross sectional area still has a role to play. Yeah, if the cross sectional area is large, this mu will be large. So that has a role to play, but the length doesn't play any role. Wave speed on a stretched string, right? And its mass per length. If it's uniform, if it's not uniform, then you have to take the derivative dm by dl. You know that from calculus, right? So now the next is how to depict wave, for example, a transverse wave in a diagram. Just like you have motion diagrams, you would like to have some diagram. So can you see that this picture actually guides you how to depict it? This is an actual string, somebody has disturbed it, but if you and immediate, because the wave speed is, yeah, right, we still have this arrow, and but we will use the word speed. The arrow only tells us the direction of the wave. That is not the direction of the speed, because speed has no direction. So you need to distinguish between a wave traveling to the right and a wave traveling to the left. But that is just a qualitative description. Wave to the right, we do not have wave as a quantity, and we do not want to say it's a vector quantity. Yeah. So the quantity is speed, and that is still scalar, right? So when we say direction, it's only for the wave, not for the speed. So if the wave is traveling to the right, we call it the leading edge because it's in that direction, and we call this the trailing edge. So if you now look at this, and this is a snapshot graph because it took a snap, and just look at this diagram now. On this horizontal axis, you can have the position, but this time it's the position in the medium along which the wave is traveling, not the position of the individual particles. So when you say the word position in this chapter, you should not confuse it with the position in chapter 15, because there the position was of the particle about the mean, about the equilibrium. Here it's the position from where the wave starts and how it travels. So although we are using the same x, but the meaning is different. Yeah, never mix this x with that x. Yeah, because x doesn't tell what it means. The context will decide it. Yeah, तो x से अपने दिमाग को जरा फ्री करें, ठीक है? वो कब उस x का कभी कभी क्या मतलब होगा, कैलकुलस में x का बिल्कुल डिफरेंट मतलब होता है, right? So the position of the individual particles, for that we will use delta y, right? Why delta y? Because this axis, the value 0, will represent the equilibrium, right? Equilibrium and delta y. So you can easily see that this diagram, this is called a snapshot graph, matches the physical picture of the transverse waves. Unfortunately, this simplicity is lost when you are into longitudinal waves. So what will change in a longitudinal wave? This or this? When you have a longitudinal wave, that will change, right? Because instead of this way, you will have motion, but this diagram will not change, because a graph will always have an x-axis and a y-axis, right? But that still be the same, because here instead of an up-down motion or instead of perpendicular motion, the individual particles will move parallel, but they will still have, each particle will still have a position, and you will still be calling it delta y. And there is only one way to plot such a thing. Yeah. So this y upward doesn't mean that it will always be physically upward. Yeah, you had this diagram even for mass spring. Mass spring was moving this way, right? But you were still plotting it. I mean, the y-axis will always be the y-axis. It doesn't mean that something has to move up for that to be true. ये बात समझ आ गई? So I can have a motion in this plane, and the graph will still have the y-axis. Yeah, labeling up. So up would mean right, and down would mean left, for example. Okay. So now this snapshot graph has one problem. You can only have this at one point in time, and that's what typically a snap means. Yeah, a snapshot. So you have to freeze time in order for this to be possible, because all the variation is in space, right? This is space, and this is also space. There is no time there. So you can have such a graph for each time point, right? So if you want to see how this changes with time, you have to create a series of graphs. So this can be at time 1, for example. Then this will be at time 2. This time 1 is not something along the y-axis, just a label, yeah, a label for this whole figure, right? And in order to help you, I would like you to pay attention. In order to instead of paying attention to the whole thing, just pay attention to one point and see what happens to that single point. So we'll be just monitoring that point, right? So because the wave is traveling to the right, so at some future time, what will happen? This whole, because this graph represents, yeah, part of the medium which is in motion, right? So that part will now move to the right. And do you see what happened to that point? Although the wave is traveling, but the atom cannot travel, or those atoms which are responsible for this motion, yeah, because the string is not moving, for example, yeah, or the water is not moving, it's only moving perpendicular. So that part will now have a different value because the wave is changing. So you can now see, can you now tell me whether this particle moved up or down? Yeah, it moved up, right? And the wave traveled to the right. So the wave is a phenomenon, it's not a thing. The wave is we call it emergent phenomena. You see a wave, but the individual particles are moving up and down, yeah? And that's what you can see, right? So the effect is there, but so if you now notice another graph, yeah, at some next time, it came back down, right? So you can see the up-down motion, and the wave is traveling to the right. So now these diagrams are not helpful. Why? Because you need a diagram for each time point. We would like to summarize all of them in one graph and to have a nice plot just like this. Just like this. And it's possible. And for that to happen, you just need to think about it. Imagine, just like you paid attention to this point, you can pay attention to, for example, can you tell me that in time, think of these as particles, particle, 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 particle. So initially, at time 0, let's say you are looking at it from here, right? You are monitoring this, and you are looking at all these particles. At time 0, which of them will come to you first? You are in front of the wave. Yeah. Which will it come first? The last one, because that's, yeah, and this will come last, right? Why? Because it's traveling to the right. So imagine a group of people traveling. So the one at the front will lead, yeah. So that's why we call it the leading edge. So leading in time as well, and that one will be, this one will be the last one. So if you now join all these points in time, but the problem is that then you have to fix position. So you have to fix a position. Let's say I'm standing there and I'm monitoring. So first one particle crosses me, then the next crosses me, then the next, and because x is fixed, now I can have a plot. But that plot will be reversed. Why? Because the leading edge, so here the x has a larger value there and x has a smaller value there. But time wise, this will have a smaller value earliest, and this will have a larger value latest. So in a time graph, this whole thing will be just flipped, and you now see it. And that's what you see. If you think about it, the leading edge was shorter and had a steeper curve. The trailing edge was longer and was not steeper. Yeah? So there you see it's the opposite. And the reason for this, that now we have time, it is still delta y, but we have fixed the value of x. So it means that you are actually, this diagram is exactly what you saw in chapter 15 for oscillation. Remember, time to position. You will need this diagram for each particle. And in each case, you will see this reversal, right? So you can now go from snapshot, it's called a history graph. What? It's a history graph, and that one is called a snapshot graph. So you can go from snapshot graph to history graph just by reversing it, but how to draw this plot will depend on the particle. Why? Because although I have the reversal, but I still have to figure out where that starts. I could have this diagram starting here. I could have this diagram starting here, but how do you decide? That will be determined by which particle you are monitoring, right? So for example, if I go back to that diagram, if I plot it, let's say, for this particle, yeah, that will start with, and let's say this is time 0. So if I start, and if this is time 0, right? If T1 is 0, and I'm monitoring this particle. So can you now tell me how that diagram should change? This will come right there because that will be my time 0, right? Let's change. Let's say this is still time 0, but I'm monitoring this particle. This is still time 0, but I'm monitoring this particle. What will happen? At time 0, I must have this point. So it means that this whole thing has to go to the past before time 0. So, I mean, this will be the easy part, but this will require a computation. Yeah. So because you will have such a graph for each particle, right? So whether it's to the left or to the right, or whether it starts from 0, depends on why it's possible. Because when you have a snapshot graph, the snapshot graph will be for a particular time. So you will know the time. Then the next thing is that you will have to decide that in this, which particle I am monitoring. So you have both the pieces of information available to you: the time for which the graph is relevant or valid, and the particle. So this should be enough to draw the histogram. And you can go the other way around. If I show you a histogram, and if I now ask you that this is for a particular point, I will use the word particle, but you should say the word point because, yeah, position. And now I ask you to turn this, to convert this diagram to a snapshot graph. So what will you do? First you will notice that this graph is for a particular point, right? And then you will say how that point, no, this says how that point moves. But now you have to say how the other points move. So it means that from this diagram, you have to go to that diagram. So this will reverse, of course, the first thing. But where will it start? Now, you have to say whether this is the particle, whether this is the, so the time of that, the time point of that must match this time, right? And then you can reverse the rest. So you will see examples. And this is how you can see it in 3 dimensions. In 3 dimensions is easy, right? So these are greater distances traveling, and these are later times. So you see, the wave is traveling, so the graph is actually moving to the right. But here it's the time. So in time, it's a different picture. Right? Can you see in time which one comes first? At 0, you have that. No, sir, sorry. Let's say you are watching it from there, yeah. So it comes first, and then this one, and then this one, and this one, right? So let's say you are given this snapshot graph. Which information is given to you? Figure 16.7 is a snapshot graph at time 0. No, at time 0. So the whole graph is for time 0. That is because in another question this could be different. Yeah, you can have t is equal to 2 seconds, for example. A wave moving to the right. So this is also important because this will change how you draw the graphs at a speed of 2 meters per second. So 3 things: the direction of the wave, the speed of the wave, and the time at which this snapshot graph was created. And now draw a histograph for the position You need to specify the position. Histograph of what? X is equal to 8. So we need to monitor which point? Now tell me, how will it start? So where will be that position at time is equal to 0? You have to look at this graph. This graph is for time is equal to 0. So at this time is equal to 0, what is the value of delta y for that point? 0. It is 0, right? 0. So it will start with 0. Then it will be the 0. It will start changing only when this point reaches that point, right? So how long does it take for this point? I should not say how long does it take for this particle to reach that particle, but because the particles are not moving, right? The wave is traveling. How long does it take for this point of the wave to reach that point? How much is the distance? 8 minus 4, 4 meters. And speed is? So the time needed is speed divided by, distance divided by speed. 4 divided by 2. So you will need to wait for 2 seconds before this point reaches. So your graph, your histograph will start at 2. Nothing can happen before 2. And after that, you just have to reverse it. So now see, just keep this thing in mind. The activity will start, this is the activity. And then you have to reverse back, yeah? So ये time 0 होगा, ये फिर next time होगा, ये होगा, सबसे आखिर में ये होगा. So इसको आप flip करेंगे, so you will have a downward graph followed by an upward graph. But the activity will start at time is equal to, and we had to calculate that time, the delta t, from the distance. So now you have to make sense of it. ये 2 से स्टार्ट हुआ है ना. दिस इज द स्नैपशॉट ग्राफ. ये तो उसने दोबारा ड्रॉ किया है ना. हाँ, ये तो उसने वही ग्राफ दोबारा ड्रॉ किया है ना. It's the same graph, so don't get confused. This snapshot graph has been shown to you for a second time. That should not change your mind. So we need the graph, the histograph at x is equal to 8, right? And of course, this axis will be time. So now we are monitoring this point, right? So for 2 seconds, nothing is going to happen. For 2 seconds, nothing is going to happen. Then this point will reach there. This point reaches there. And then the activity has to reverse. Is that easy? You just need to understand the concept of, the nature. Those two have, here position is frozen, here time is frozen. So if you remember that a snapshot has a frozen time and a histograph has a frozen position. And how do you go back? Let's say I give one this and I want you to draw this. You just have to reverse this whole process, right? So this graph is only for x is equal to 8, and that graph will require you to have the value of delta y for each x, but for a fixed time. So what is the fixed time here? Time 2. So you can have that diagram drawn immediately for time 2. But what if I asked you to draw it for time 0? You have to change. You now have to find the difference. Yeah, and then yeah. So for example, if this was for time 2, let's say I had asked you to draw this diagram for the same x, starting from the same x, but I want you to draw this for time 2. So how will this diagram look? Time 2. ये तो time 0 पे है ना. No, if I want it to be at time 2, it will be there. Yeah? It will have traveled, right? Just give me just a second. And we can pick one example, one question from the exercises, right? I would like you to practice both, going from a snapshot graph to histograph, and from a histograph to snapshot graph, and just reverse everything. Yeah, you just undo everything. So The next is how to visualize a longitudinal wave. This snapshot graph is great only for transverse waves. Why? Because the physical picture of the medium matches what you see in the graph. I told you the mathematical graph will still look the same even for a longitude, because you still have x-axis and you still have y-axis. That is not going to change. We have not invented any new methods of graphing, but the physical picture has to change, right? So now, how will it change? So now tell me. First, this is for time 0. Snapshot graph at time 0. So it means that whatever you see there, at time 0, this particle at 0, this particle is at 0. 0 means equilibrium, right? So all these particles are in the equilibrium. All these particles are in the, these particles are to the right of the equilibrium. Why? Because it's a longitudinal wave. So let's say a wave is traveling to the right. So these particles are to the right of the equilibrium. These particles are to the left of the equilibrium. This particle is most to the right. This particle is most to the left. So now we have to start here. So equilibrium position, you just draw lines and identify the equilibrium positions. So can you now tell me at time 0 why the first points are still at the equilibrium? They never changed. Because this point is actually that point, but I'm just projecting it. So this point and this point, they both are 0 at 0. So they remain at the equilibrium. Just monitor this point. This is a bit to the right. It moved a bit to the right from the equilibrium. That was the equilibrium position, but at time 0, it means that that was in the past, before time 0. At time 0, that point moved a bit to the, this point moved the most to the right. It moved the most to the right. This point, no, this also moved to the right, but in the same way. इन दोनों का राइट की तरफ मूवमेंट सेम है ना, तो जितना ये मूव हुआ है उतना ही वो मूव हुआ है. एंड दिस पॉइंट इज स्टिल एट द equilibrium. Now this point moved a bit to the left. This point moved the most to the left. This point moved a bit to the left. क्योंकि ये दोनों सेम है ना. This point didn't move. So now we have a picture. Now, at one second later, you know the speed, right? What is the speed? 1 centimeter per second. So you should know how much to move. This distance was calculated with the help of that speed. Yeah, I change that speed and this distance will change. Now, can you tell me what happens at t is equal to 1 second? At t is equal to 1 second, because the wave is traveling, this whole graph has to move to the right. How much? 1 meter. In 1 second it will move. So all these points, you don't need to redo this work. All these points will have to just move to the right without doing anything. अब देखें, देखो ना, ये इधर आ गया, ये इधर आ गया, ये इधर आ गया, और पीछे से एक ऐड हो गया क्योंकि नीचे ये भी आ गया. ठीक है ना? टाइम 2, again that whole thing move to the right. ठीक है ना? यहाँ से equilibrium ऐड तो होता है because ये पीछे सारे zeros आ रहे हैं. So it's so easy. So the mental picture you have for a longitudinal wave has to be this, right? And the graph is the same. The graph doesn't care whether you are dealing with a longitudinal or transverse. And this is that wave in the sporting event, right? Right. So it's only to show that. So the problematic part is that you get the energy from your own body. Yeah, that is not what is happening in a wave. But think of it as information. You get the information. So it's not an energy wave, it's an information wave. So what you see in a sporting event, because you don't have the information, you saw someone else, or maybe he shouted, and actually you're following it in that sense. So it's a wave in that sense. How do we represent a wave mathematically, right? So you know that in oscillators, you have that particle oscillating, and you need a variable like x or y. Remember, for the spring mass we had x. Yeah, for the vertical spring we had y, and for the simple pendulum we had s, the arc length. So each time you will need some variable. So here we have the variable x for the position along the wave and delta y for the disturbance. So it means that, I mean, just we cannot just say delta y all the time, right? So we need a new symbol d for the disturbance, and this disturbance, you think of this disturbance as a function. But this function will depend on two things. It will depend on the position, because you need to know where in the wave you are monitoring, and also the time, at which time. So it will be a function of x and t. So you can, I mean, you can even think of it as delta y, because this is the function notation where you d of x comma t. Delta y is not a function, right? It's a variable. So a counterpart of this will be delta y. You will see this, you will learn this in calculus. You just have a bar, and here you say x and t, right? So when you have a variable associated with some condition, you put a bar and then you write the values. But if you have a function, you just use the brackets. Yeah? It is stupid to say delta y of x and t, because that delta y is not a function, right? And this is how a sinusoidal wave. So just like we want simplicity, so in oscillations, the simplest oscillation was simple harmonic motion. So the simplest wave will be when the initial disturbance was sinusoidal, then the wave is also sinusoidal. So you have a sinusoidal phenomena along x and along y. Now, how do you characterize this? You know how to characterize a sine wave along time. How do you characterize it? You know, this is time, this is amplitude, this is just a repetition of chapter 15. Yeah. So a history graph will always look like what you saw in chapter 15, sinusoidal. And you will use the same language, yeah? Frequency, time period, right? Amplitude. How about a snapshot graph? It will still be sinusoidal, because remember, the wave is still sinusoidal. So as a function of time, it has to be sinusoidal. As a function of position, it has to be sinusoidal. But the point is that how do we write it mathematically? You know how to write the function for oscillations mathematically. How did you write it? Do you recall that? So you said, here I'll just write d, right? So d of t, and let's fix the time, fix the position. So let's call it x0, 0.0. I'm just monitoring one point. And t is still a variable. So how will it look like? I will still have an amplitude. Now, one thing changes from oscillation to wave. I told you that in order to write a sinusoidal function, you can either have cosine as your standard or sine as your standard. So if you have any other phase, you can just write that as phi naught. Yeah. So cosine of something plus phi naught. Unfortunately, the convention in wave is different, because these theories develop differently. So here we will use sine as our template, not cosine. That's only a convention. Yeah, there is no mathematical reason for that. So the meaning of phi naught has to change, right? Because for a sine, the phi naught will have one meaning. For cosine, it will have another meaning. So I'll have to say sine. Sorry, even in a wave, yeah? Because this is a wave chapter. So I'll use sine, and what will I do? T plus phi naught. और यहाँ पे क्या था? I either have to say omega or 2 pi by t, and I know 2 pi by t is just omega. Now you need to construct this same formula for the other case. When I freeze time, let's freeze it to t naught, and I want to keep the position open, variable. Here t was the variable, x was fixed. Here t is fixed. So now can you construct it? It will still have the amplitude, right? That should not change. It will still have phi naught, because phi naught is when, yeah. So what will happen here? What will you have? No, here the free variable is t, here the free variable is x. Of course, this phi naught will depend on this x naught, and this phi naught will depend on this t naught. In that sense, they will be different, right? So you can think of it as phi for t naught, for x naught, and phi for, but let's ignore that point for a while, right? So what will I have here? I will still have, but what will I have here? I cannot have t here because t is the time period. Now I need the space period, wavelength. So once you understand the math, you can just apply it to any problem. Yeah, we constructed the formula without doing any derivation. Why? Because we understood the meaning. Time period, space period, wavelength, right? So, and you can see the diagram, right? Because this is position, this is disturbance. I will not allow this, right? Because d, if d is a function, you cannot write d there, right? So what you can do, that you can put this d there, for example. You can place the label of a function on the graph somewhere, but here it has to be d of x comma t naught, the fixed time. So crest to crest, trough to trough, you have wavelength, right? And now you can see something interesting. Let's say you have these different snapshot graphs for different points. T is equal to 0, t is equal to a fourth of the period, t is equal to half of the time period. When I say period, I mean half time period. 3/4 of the period, full period, and just monitor one point. Just monitor this point. What happened to this point? It moved to the right. Then it moved to the right, and then moved to the right, and then it reached another peak. So how much distance has that point traveled? 1 lambda, but how long did it take? 1 time period. Now you can construct something new. You now know that if I have distance here and if I have time here, I should get speed, right? So I can now have a formula for speed of the wave, not speed of the particle, right? So wave speed, and I can write here lambda, and I know that lambda needs, so now I have formula for free, right? And this you can write as lambda cyclic frequency, and you can even write 2 pi by omega, all those things like that. Yeah. So now this formula, distance divided by time, lambda per t, and you have this formula. Interestingly, this formula didn't use the medium. So now you have seen two formulas for the speed. One, this one, and one, the one which you had. So you need to know how to interpret these formulas. This was for a specific type of wave in a string. That's why it used, so you cannot use this formula, for example, for longitudinal waves or for electromagnetic waves. But this formula didn't need any details of the medium. It didn't even need the type of the wave. We didn't even need to know whether we are dealing with the mechanical waves or electromagnetic waves or gravitational waves. Gravitational waves, by the way, another type. You can even have matter waves, right, in quantum mechanics. So this formula applies to everything. And I'll just give you an analogy. You need to understand appreciate the quality of a formula. So even in chapter 15, we saw two types of formulas, if you remember. We saw this formula, if you remember, that Vmax, remember, the maximum velocity of the particle was. This formula didn't require you to know whether it's a spring mass system or a pendulum, because this was done purely from the kinematics. But on the other hand, this formula, if you remember, for example, G divided by L or L divided by G, it was for the pendulum. And then M divided by K, those formulas, they were for specific. So this is the highest quality formula because you can apply it to any case, right? So you need to know how general a particular formula is. So you can apply this to light, you can apply this to gravity, anything. Yeah, gravitation. You know gravitational wave, right? Why do I say gravitational wave? Because the Newtonian mechanics which you are learning in this course, like Newton law of gravity, Similarly, Coulomb law, yeah, they dictate somehow that they claim that everything is happening simultaneously. So, for example, the gravitational force between the Earth and the Sun will immediately cease to exist if I remove one of them. Let's say I remove the Earth, or if I remove the Sun, there will be no force immediately. But this is something which is wrong. Yeah? So Einstein picked this point, and he gave us the theory of general relativity. And there, what happens is that whenever you introduce a huge mass into the space, the properties of the space start changing. It has to experience that mass, and that is what we know as the bending, yeah, bending of space time. So that effect has to travel to the Earth before it can act on Earth, and that cannot travel faster than the speed of light. Yeah? So you can even have gravitational waves. This formula applies even to that, right? Because it doesn't care about the time. So now we need one more formula nicely. You already know the relationship between the angular frequency, the cyclic frequency, and the time period, right? This is what you know from chapter 15. Now we need a similar formula. So we'll keep 2 pi, and instead of t, now I have wavelength, and now I have a new quantity. So this will be the counterpart to angular frequency. We cannot call it frequency because that is relative to time. So the name which physicists found out and they recreated is called wave number. So if I ask you what is the interpretation of omega, so you will say 2 pi by time period. What is wave number? 2 pi by lambda. But it is easiest to give meaning. It is not easy to give meaning to omega because it is radians, 2 pi radians. So you can think of it as, if I asked you the meaning, omega, the angular frequency, is the number of radians per time. What? Number of radians per time. So k will be the number of radians per length. That is not very, very easy to understand. Let's remove the 2 pi from it. So remove the 2 pi, so I'll be left with f. So f is the number of cycles per time, and k divided by 2 pi will be the number of cycles per length. And cycle is just oscillation. So you can say number of oscillations per time, number of oscillations per length, or per distance. So now I can write this final formula. D of x comma t is amplitude. Sine, we are not using cosine anymore. And phi naught is still there. And because phi naught requires both x and t to be 0. That's why phi naught is always phi naught, right? And then kx minus omega t. Now you must be asking, remember omega has been replaced by k, t and x. Why do we have a minus here? Why not kx plus omega t? Now this requires you to recall some of the calculus. So in calculus you have been dealing with graphs, right? Graphs of a function. What happens or how do you represent a graph translation to the right? F of x minus something to the right. If you want to replace that minus with plus, then you have to shift the graph to the left. So if the wave is traveling to the right, it has to be minus. Yeah. So calculus answers the question. And it also means that if you happen to know that the wave is traveling to the left, you'll have to write plus there. What if you have a medium in which there are two waves, one moving to the left and one moving to the, like you fix the string from both sides, standing waves, although we are not getting into that, then you will have to add two terms, one for the wave to the right, and then you have interference of two waves, right? So the math will always help you. Let me just ask you a quick question. What is the period of this function? Yes? 2 pi. Yes and no. Yes, if you think of t as a number in calculus. right? This function is nonsensical if t represents the physical time. So before you tell me 2 pi or 1 pi or 1 or 2, you have to question that what I wrote down is not allowed to write. Because sine, cosine, exponential, they are mathematical functions and they only act on real numbers. T is not a real number, right? So it's a piece of crap which I have written. Just because I wrote it doesn't make it true, yeah? So you have to write t by something. So you can say t by 1 second, for example, yeah, or t by, yeah, so on and so forth. So if I write t by 1 second, then what is the period? 2 pi seconds. 2 pi seconds. Now tell me, what is the period now? And I want you to recall calculus again. What happens when you stretch the function? Okay, before I do this, let me try something else. Let's keep that to 1 second, right? And ask the question again. So what is the period of this function? 2 pi seconds. Now let me do something. What is the period of this function? Have you stretched it or have you compressed it? You compressed it, yeah? Because you multiplied by 2 pi, and 2 pi is larger than 1. So अब इसका period क्या हो गया? 1 second हो गया. 1 second हो गया कि नहीं? अब एक काम करें. So I want the math to speak for me. I don't want to bother my brain too much, yeah? And you can apply the same logic here, right? Sine x by 1 meter. What is the period? 2 pi meter. Okay? So don't trust me, trust the math, right? Okay, this part is not included in the course, but I just have to mention one thing so that if there is any curiosity, there will be no math there, but you must be wondering, how does the string, so it's easy to understand longitudinal wave, although it's difficult to visualize, but it's easy to explain how longitudinal wave is possible. Why? Because you have the example of spring mass. So if you think of a medium as being composed of those spring mass, because you know atoms are particles and bonds are springs. So even though you cannot see it, you can still explain it, right? Like that. So I mean, you just imagine. Let's say you have a troop of, let's say, 100 soldiers. They are lined up, and you just start, yeah, wiggling one of them. So what will happen? You just do that. Yeah, you can't do this to soldiers in this country, but just imagine. Yeah, because you don't know what will happen after that. So let's say you do that. What will happen? Imagine they can touch each other, right? So although you started that oscillation at one end, they will immediately. So you know this is possible. The oscillation is possible to reach the other end, right? So that's why I say that longitudinal wave is easy to explain, right? But now, how can you explain the transverse wave? I mean, imagine those soldiers moving up and down. I mean, jumping. There is no way that yeah. So how can you now explain the transverse waves in a string? Because the soldier analogy doesn't work, right? So how will you explain that?
The soldiers are connected.
Yeah, then it is possible, right? So they must be connecting each other. So that is the model which you need to understand. So when you look at a string, it is not just a bunch of particles, they are connected by strong bonds. And when you want to disturb one of them, that bond will react. So that energy will not be isolated. The energy will be transferred to the fields between the atoms. So the energy, let's say you start the oscillation here. So when you start this motion here, that whole field, that electric field between the atoms. It gets disturbed, and that's why the neighboring and that's why you have a tension in the whole string, right? Why do you say tension in the string? The tension is everywhere, right? So that means that these this these individual oscillations, they will somehow team up in a way to give you the final transverse wave. And if you want to see the derivation, I mean, if you just think about one small segment, although you have a tension in the whole string, but that tension has to vary a little bit. So the tension on one end must be larger than a tension, and this difference will actually carry the thing. And I'm leaving the derivation, but just to give you one example, remember we just saw this formula, remember? What was the formula we saw? Wave speed, lambda divided by period. Now do something. Multiply and divide by 2 pi, right? And now think about, this will give me 2 pi by lambda, but in the denominator, right? That will give me 2 pi by t, but in the numerator. So that should give me the angular frequency divided by the wave number, right? Angular frequency divided by the wave number. And this formula can be derived by this step to give you that Ts by, so that Ts by mu square rooted is just one particular case of this formula. And you can have a similar formula for the speed of sound, for example, right? This will still be for the speed of sound, you can still write this down, but this will change to some other thing. And I would highly recommend that you solve this example, right? इसमें से क्या किया हुआ है? A very long string, mu की वैल्यू उसने दी हुई है, linear density है 2 grams per meter, is stretched along the x-axis with a tension of 5 newtons. So tension is given, and this by this should immediately give you the wave speed, right? And then at x is equal to 0, it is tied to a 100 hertz simple harmonic oscillator, right? That vibrates perpendicular to the string with an amplitude of 2 meter. Yeah, delta y maximum value. The oscillator is at its maximum positive displacement at t is equal to 0. Write the displacement equation for the traveling wave at so I mean, I will also provide my solution in the notes, but you, before that happens, you should read the textbook. He has explained it. All these formulas which I just gave you, sine omega t, sine kx minus omega t, yeah, this one, they're all used there, right? So I will highly encourage you to read the solution. So now we move on to the sound waves. It was easy to explain longitudinal waves in a solid medium like a string, yeah? Because I gave you the analogy of spring mass. Now it is difficult to explain those same longitudinal waves in the air, for example. You can explain it in water, for example, because you can imagine water molecules to be touching each other, but the air molecules are not touching each other, right? They're just like those soldiers away from each other. So how do you explain? So just like it was possible here, although the particles are not touching each other, but the good news is that the particles, you have the kinetic theory of gases, right? They are moving very rapidly. So the soldiers are not moving like that, and the water molecules are not moving like that. So the thing which goes in favor of longitudinal waves is that the gas molecules, although they're not touching, but they're all the time in motion. And so it means that anything you do to one part of the air or any gas you have in mind, and let's say this is that initial source, the loudspeaker. So you now change. What do you do immediately in that region? You change the pressure. And what do you mean by the pressure? Pressure is actually force per area causing from those collisions. So because you press the air and there's nothing pressing from that side, so you will actually cause a compression in a region of space. So you make the molecules or particles of the gas get closer, that you actually increase the density. That is what we mean by high pressure. Now, this part of the region, you have done nothing to it, but this pressure, pressure has its own laws. So that pressure will now influence this part. So it's actually, think of the sound as a pressure wave, yeah, or you can think of it as a density wave, yeah, high density. So now you can explain why you were told compressions, rarefactions. Compressions. So this is compression, but what happened there? Because you see those particles moved there, so you had a rarefaction, and now this will be compression, rarefaction, so on and so forth. And sound waves are not just the ones you hear. There is ultrasound, right? So they are so high frequency you cannot hear them, but they are used, for example, in detecting, yeah, non-intrusive. आप सारे इसी प्रोसेस के थ्रू जो है ना, so you should thank the wave phenomena. Electromagnetic waves आपको पता है ऑलरेडी सारी, ठीक है. So इसका speed, wave speed, जो c है speed of light, it's actually a wave speed, right? C, wave speed. And this is a proof that wave itself is a phenomenon, because there's no particle moving and you still have speed, yeah, wave speed. उसमें तो आप कंफ्यूज हो सकते थे कि हो सकता है मेरी अंडरस्टैंडिंग, यहाँ पे तो आपका अंडरस्टैंडिंग regardless of what you understand, C has nothing to do with particles, right? And these are actually some ranges, microwaves, AM radio, ये आप खुद कर ले, ठीक है. और इसने example दिया हुआ है how to calculate. So the one thing which you need to understand is the what we call the index of refraction. So this is important because C, the value the value of the speed of light, the wave speed, that is only in the empty space, right? So whenever you want that light propagation in some medium, the medium will interact with that with those photons, and what will it do? It will slow down. It will slow down in most cases. In some cases, it can even speed it up. So you need to figure out how the speed of light changes in a particular medium, and the ratio of these two is what we mean by the index of refraction. So you just divide the speed of light by the speed of that same light. So speed of light in a vacuum and divide that by the speed of light in that material, so you get the refractive index of that material. And this list, so now can you tell me from this list in which medium the speed is the lowest? The lowest? Air. Because this is a vacuum, yeah? Here, in all these, so the highest is in diamond. Why? Because, no, I think it's C by V. It's not V by C. The diamond would have been the highest if this was V by C. It is C by V. Yeah, so diamond is the lowest. Then glass. So actually in the air it's the highest. It's the highest, right? And it is now the reason why. So if I were to define it, I may have defined it like V by C. Now you should know why they defined it in this way. Because you don't want all of these numbers to be smaller than 1, right? बस समझ आ गई. तो C को न्यूमरेटर में इसलिए रखा है कि सारे नंबर्स क्या आ जाएं, larger than 1 आ जाए. And you can even calculate the wavelength in a material by this formula. Wavelength in a material is what? Speed of wave speed divided by frequency in that material. Now frequency in the material will not change. Why? Frequency cannot change from one material to another. Why? Try to recall the discussion I started in the start of this chapter, this lecture. How does the wave propagation start? From that initial source, and that will have a frequency. And the definition requires all these oscillations to be of the same frequency, because you don't have any other source, right? So frequency will always be. नहीं वो क्या करते हैं रात को मुझे. So frequency cannot change, right? Frequency only depends on the source. तो अब देखो ना, अगर फ्रीक्वेंसी चेंज नहीं हो रही है और स्पीड चेंज हुई है, so the only thing that can change in a medium is the wavelength. There is no way frequency can change. Frequency will only change when you change the source. और source तो हमने change किया नहीं है, light तो उधर sun से आ रहा है. We need to change the sun if we want to change the frequency, right? So लेकिन ये एक कलर की बात हो रही है ना, different colors हैं. So maybe you have a source which can only give you, for example, 3 colors. So अब उसके बाद इस फॉर्मूले को पिक करें, so you have the lambda in the vacuum divided by the refractive index, and that gives you lambda in the material. So अब आपको समझ आ गई कि ये क्यों, why does this phenomena occur? You have one light and all these colors, why do they disperse? Because this medium changes the speed, and the change in the speed, you just saw it, depends on the wavelength, right? Frequency तो सबकी same है ना, तो इसलिए you have the bending depends on the speed, right? And that depends on the wavelength. Okay, ये मैं skip कर रहा हूँ. इसमें सिर्फ ये है कि अगर आप ये follow करें derivation को, which I am skipping, so मैं आपको सिर्फ final formula बताता हूँ. Just like we had a formula for the wave speed in a string, we can have a formula for the wave speed of sound in a medium. तो वहां पे तो Ts था, tension in the string and linear density of the material. यहां पे क्या होगा, चेक करें, density of the medium. अब आपको समझ आएगी वो लिस्ट में क्यों फर्क था स्पीड में. और ये you have this is something which is similar to pressure. So bulk modulus, it tells you how much pressure that medium can hold, right? So you have all these formulas. वो जो न्यूटन लॉ फॉर स्पीड ऑफ साउंड, वो भी इसी से आया था, उसने एयर के लिए किया था, समथिंग लाइक दैट. Now this thing, waves in 2 and 3 dimensions. अब आपको पता है कि जो वेव फिनोमेना अभी तक जो हमने स्टडी किया है वो सिर्फ एक ही डायरेक्शन में, राइट, जस्ट आउटवर्ड. But you, for example, in the air, this wave propagation can be in all 3 dimensions, right? In water, it can only happen in 2 dimensions. In a string, it can only happen in 1 dimension. But remember, why does it happen in 1 dimension? Is not because of the oscillator, but because of the medium. So if the medium is 3-dimensional, the wave will also be. So you can have waves in 2 dimension, 3 dimension, depending on the medium, right? So it means that you can have spherical waves. So you have these different wave fronts. By wave front, we mean, just remember, just like we fixed one position along the x-axis, right? So fix one position. So imagine in 2 or 3 dimensions, you can fix one position away from the source, and if it's a spherical wave, so in that distance you can have a point here, a point here, so you have a whole sphere of particles in the medium which will have the same distance from the source. Do you get that? Let's say here is the source and wave phenomena is occurring in all directions, so I can imagine a sphere of particles in the medium all with the same distance from the source. Because they have the same distance, they will have the same energy receiving from the source. That is what we call a wave front, right? Wave front. So what do you mean by a spherical wave front? That's sphere. So what will happen in a, for example, 2-dimensional wave? Imagine water. In water, you cannot have this spherical wave front, right? Because it will only be in 2 dimension, right? So you can have a circle. That will still be a wave front. In a string, what will happen? You can have a plane of particles, some up, some down, some in at the equilibrium, things like that. So whether it's a plane, whether it's a circle, yeah, whether it's a line, whether it's a line, whether it's a circle, whether it's a sphere, you just call it a wave front. टाइम हो गया कुछ का, ठीक है। तो अब अगला लेक्चर होगा हमारा या नहीं?